On April 24, 2026, DeepSeek released V4 Pro. It is a mixture of experts model containing 1.6 trillion total parameters, with 49 billion activating for any given token. This architecture positions an open-weight model directly alongside the performance ceiling of proprietary frontier systems. On the SWE Bench Verified evaluation, which tests a model's ability to resolve real-world GitHub issues, V4 Pro scores 80.6%. This effectively matches the repository-level engineering performance of Claude Opus 4.6. This chart compares inference costs per 1 million output tokens. While frontier models typically range from $25 to $30, DeepSeek V4 Pro drops to $3.48. The result is near-identical coding performance at roughly 1/7 the price. Furthermore, V4 Pro handles a 1 million token context window. This capacity is treated as a default functional standard for the API, rather than a restricted high-premium feature. These benchmarks were achieved despite strict hardware constraints. DeepSeek trained the model utilizing domestic Chinese silicon, specifically the Huawei Ascend 950 series, instead of the latest NVIDIA accelerators. The existence of V4 Pro suggests that the compute wall, the assumption that frontier performance requires unhindered access to elite hardware, can be bypassed. This output is driven by algorithmic efficiency rather than brute force hardware scaling. DeepSeek utilized 3 specific architectural redesigns to reach this efficiency: hybrid attention, manifold constrained hyperconnections, and on-policy distillation. Achieving this level of logic on restricted silicon shifts the competitive pressure. It suggests that architectural efficiency, not just raw compute access, defines the current performance ceiling. To process a 1 million token context window, DeepSeek had to address the memory bottleneck of standard multi-head attention, specifically the critical key value, or KV, cache. In standard attention, the model must track every token's relationship to every other token. At 1 million tokens, this memory overhead expands quadratically, which frequently triggers out-of-memory failures on standard GPU clusters. DeepSeek addressed this by abandoning standard full attention for a 2-part compression system known as hybrid attention. This represents the first stage, compressed sparse attention. The model maps thousands of tokens into compressed blocks, significantly reducing the active memory footprint. To retrieve information, a Lightning indexer performs rapid top-K selection. It enables sparse reads of the compressed data to find relevant context without expanding the full sequence back into memory. The second stage is heavily compressed attention. This applies a 90% compression ratio, maintaining dense attention over the stream, so the model can still capture global relationships across the entire million-token window. This hybrid architecture allows V4 Pro to operate using only 10% of the KV cache memory required by its predecessor, DeepSeek V3.2. There is also a computational benefit, as the model requires only 27% of the single-token inference flops to process that million-token context. For engineers, this massive memory reduction allows a model to ingest a 500-file repository in a single pass, tracing call chains across dozens of modules without the need for external vector databases. Reducing the KV cache footprint by 90% changes the fundamental overhead of long context tasks. It moves million-token windows from a niche, high-cost edge case into a scalable operational standard. During pre-training, scaling a mixture of experts model to 1.6 trillion parameters introduces the risk of catastrophic divergence, where the mathematical gradients used to train the model shall explode and crash the system. To increase the model's expressivity, DeepSeek used hyperconnections, which expand standard residual connections into multiple parallel information streams. Without constraints, these connections create signal amplification loops. In DeepSeek's early tests, signals expanded by over 3,000 times their original value, instantly destabilizing the training process. DeepSeek addressed this with manifold-constrained hyperconnections, or MHC. The system uses the Sinkhorn-Knopp algorithm to bind residual mapping matrices to the Birkhoff polytope. This forces the operations to stay within a set of doubly stochastic matrices. This ensures the matrices remain non-expansive. Spectral norms are bounded, which limits signal amplification to a stable 1.6 times. The team paired this with the muon optimizer, which offers faster convergence and higher stability at the trillion parameter scale compared to standard AtomW. They also integrated FP4 quantization-aware training. This optimizes the model weights for high-efficiency deployment during the pre-training phase itself. These stabilizations allowed a continuous training run across 33 trillion tokens, removing the need for the massive hardware retry budgets usually required at this scale. The result proves that architectural stability is a solvable mathematical constraint problem. It does not necessarily require throwing more hardware at random training failures. In the post-training phase, DeepSeek modified the standard approach to reinforcement learning. Training a single model simultaneously on math, code, and dialogue typically causes capability dilution and gradient interference. V4 uses a specialist then distill paradigm, which begins by isolating training into specific domains. First, the lab cultivated over 10 independent domain experts for tasks like math, code, and agent behaviors. Each expert was optimized individually using group relative policy optimization. In the second phase, on-policy distillation merges these isolated experts into a single student model. The distillation process employs full vocabulary logic distillation via reverse KL divergence, mapping all 128,000 vocabulary bins from the expert directly to the student. Transferring the entire probability distribution captures the expert's nuanced uncertainty and confidence levels. This allows the student model to inherit complex reasoning paths without capability conflicts. For subjective tasks where correct answers are hard to verify with rules, DeepSeek introduced the generative reward model. This model allows the network to both generate and evaluate its own reasoning trajectories against strict rubrics, reducing the need for massive human annotation teams. This specialized pipeline explains V4's performance profile, a massive advantage in technical logic, but hard limits in other areas. Because the model relies on specialized data trajectories rather than sheer parameter memorization, it trails frontier models in simple factual recall while excelling in programming and math. This makes V4 a specialized technical execution engine, optimized for completing complex software and mathematical work rather than retrieving general facts. On-policy distillation demonstrates a viable path for multi-objective optimization, changing how frontier labs approach the synthesis of competing model capabilities. The economic impact of V4 Pro is visible in its API cost structure. It charges $3.48 for output tokens and just 14.5 cents for cached input, compared to $30 or more for models like Claude Opus or GPT 5.5. This cache hit pricing makes repetitive system prompts and recursive tool calling cycles extremely inexpensive to run at scale. There is a trade-off in intelligence density. V4 Pro often requires longer generation trajectories, more output tokens, to achieve the same reasoning result as GPT 5.5. However, even when factoring in higher token volumes, the 7x cost differential makes multi-step agentic pipelines economically viable for high-volume enterprise tasks. V4 also introduces persistent reasoning states, meaning the model's chain of thought is preserved across multiple tool calls, so it doesn't lose context mid-task. The need of multimodal integration allows it to process UI screenshots and code simultaneously, avoiding the overhead of external vision adapters. These optimizations were developed to bypass significant hardware embargoes and silicon limitations. Achieving frontier-level logic on domestic hardware demonstrates that hardware constraints can be mitigated through software engineering, challenging the advantage traditionally held by labs with unfettered access to elite clusters. As raw intelligence becomes commoditized, the bottleneck for enterprise AI shifts. The advantage no longer belongs simply to those who buy the best model, but to those who engineer the most sophisticated orchestration.